In this lesson, what we're going to do is just a quick demonstration of what the difference in behavior between the rising edge D flip-flop, the falling edge D flip-flop, the transparent active high latch, and the transparent active low latch. We're just going to show exactly based on different values of D and the clock, what happens on the output. Now, real quick, before we get started, let's talk about, first of all, whenever we talked about the D flip-flop, remember that there was two kinds. There was the rising edge, and there was the falling edge. Now, how might you see these indicated on a truth table? In other words, most of the time, whenever we see inputs on a truth table, we see a 0 or a 1. Well, these are two new conditions. They represent the instant something is changing. You could see one of two different types of signals. A rising edge you may actually see represented with a small step up, to indicate, well, the transition from a 0 to a 1. So that would indicate that we want to capture that instant. Falling edge has a similar one, a step down, right? You may, however, also see an up arrow or a down arrow to represent those transitions. In general, though, what you're looking at is rising edge, falling edge. Those are moments in time where the signal actually is in transition, and it's not the same as just a solid 0 or a solid 1 that you would find on a truth table. All right, so let's do a quick timing diagram of what you might see on a D flip-flop versus a D latch. So I'm going to draw just, well, what you might see on D or the clock, just give you, as time is going on, some patterns that we might see. So let's just say, I don't know, how about D is just changing kind of randomly here. All right, so those are the values we've got on D. Now, for the clock, what we've got is, I'm just going to, this is not necessarily the way that a clock is going to look, but I'm going to make the clock, I don't know, it's just going to change up and down a little bit. Now, if you're trying to copy this at home, who knows? You may or may not get something similar to this, something probably different, but the operation should show you exactly how, or our description should show you exactly how these things are working out. So what I'm going to do is I'm going to put a dotted line to represent exactly the moments we are getting these rising edges or falling edges on the D latch, excuse me, on the clock going into the D latch or the D flip-flop. All right? All right. Now, what we're going to do is we're going to, using this drawing, we're going to show what it looks like whenever you have a rising edge triggered flip-flop. We're going to do it, if we put these signals into a rising edge triggered flip-flop, we're going to see what it looks like if we put these signals into a falling edge triggered flip-flop, and we're going to see what happens if we put them into a transparent latch, active high and active low. So there's going to be 4 circuits that I'm going to go do down here. Now please understand, these are 4 different circuits. So it's not like you can get a D latch to behave one way or the other. What we're going to do is have actually 4 independent different types of circuits. So let's start with the rising edge triggered latch or flip-flop, and what we're looking at is Q. So this is what Q looks like. This is how Q is going to behave for a rising edge latch. Now, remember the definition from the previous lesson of what a rising edge flip-flop did. What it did was it copied D to Q the moment we had a transition from a 0 to a 1 on our inputs. All right, so that means we are going to copy D to Q at that rising edge, at this rising edge, at this rising edge, at this rising edge. Now, what happens between those rising edges? Not a thing. Q stays exactly the same. So it's kind of like we took a picture with our camera. We took a picture at this moment, then we took another picture at this moment, then we took another picture at this moment, and then took another picture at this moment. What happens in between is whatever the captured value was, it's going to stay on our output Q until we take another picture. Now, what happens before this period? Well, before this period, we really don't have an idea. There's a couple of things that we could do. You know, in our drawing here, what we could do is we could just leave it blank, so, you know, we don't know. But a very common thing to do is to just simply put both the logic 1 and the logic 0 levels and just put these little transitions in between. Look like little X's, okay? So up until that moment, we have no idea what's on Q. Now, before that, or after that, excuse me, at that moment, what is D equal to? Well, at that rising edge, D is equal to 1. So we have stored a 1 to Q, and that 1 is going to stay on Q until we get another rising edge. So starting at that moment and until that next rising edge, we know that we've stored this 1 at that moment. All right. Now, what about the next rising edge? Well, the next rising edge occurs right here. What's D equal to at that moment? Well, at that moment right there, D just so happens to equal a 1 again. So what we're going to do is we're going to store a 1 again, and that 1 is going to stay on it until we hit the next rising edge. At this next rising edge, what is D equal to? Well, D is equal to a 0 at this next rising edge. So the new value stored to Q is going to be a 0, and we're going to store a 0 on there until the next rising edge. At this rising edge, so we've got a transition from a 0 to a 1 at that moment, what is D equal to? Well, at that moment, D is equal to a 0, so we are going to store a 0 again. And that 0 is going to stay on there until we get another rising edge. All right? So there is what our Q looks like whenever we have a rising edge D flip-flop storing the values based on that sequence of inputs. All right? Think it's going to look different for a falling edge? Yeah. So now a falling edge. What does Q look like for the falling edge? Well, for the falling edge, what we're going to do is we're going to capture D to Q the moments we have these 1 to 0 transitions. And so I've got a 1 to 0 transition here. I've got a 1 to 0 transition here. I've got a 1 to 0 transition here. And I've got a 1 to 0 transition here. All right? So at those little X's, that's where our falling edge D flip-flop is going to capture the value of D. So at this first one, at this moment, whenever we take the picture of D, what is D equal to? Well, at that falling edge, that 1 to 0 transition, D is equal to a 0. So we first store a 0 on D until we get to the next falling edge. At this next falling edge, this 1 to 0 transition, right there I've got a 0. So I'm going to store 0 again until the next falling edge. At this falling edge, wow, we stored another 0. So D is equal to 0 at this falling edge. So it's going to store a 0 until the next transition on the clock. On the clock, I've got a 1 to 0 transition. Now D is equal to a 1, so here we are going to store a 1 on Q. All right. So there are our values for a falling edge Q based on that sequence of inputs. So we put the same sequence of the same pattern into a rising edge D flip-flop and into a falling edge D flip-flop. We got very different outputs in Q, didn't we? All right, so these two right here are edge triggered. Now what we're going to do is transparent. All right, and the transparent, well, we have, remember there's active high and active low. We're going to figure out what Q is equal to for both of those. Now, starting with the active high, What happens, what allows us to pass D through to Q? Whenever the clock is high. Well, the clock is high between these two dashed lines. So whatever D is equal to, from the time that clock goes high until it goes low, we are going to pass that D straight through to Q. All right? So this little step right there is going to be mimicked on the output Q. Now, this period of time, the clock is low. It's not high, so it's low. So whatever the last value was that was captured from D, that's going to stay. Notice D can change around all it wants to. This value is going to stay latched. It's going to stay holding. Okay. This period of time right here, the clock goes high, so the value that's on D gets mapped to Q. So this D starts out as a logic 1 and then steps down to a 0. So I'm going to start at a logic 1, step down to 0 in the same path that was done on D. Connect this up. Now, as soon as the clock goes to 0, whatever the last value was that was on D, that gets latched onto Q. All right. The clock goes high again here, so whatever D is equal to, and D just so happened to equal a constant 0 across there, so we're going to have a constant 0 on Q. All right. For this period of time right here, between these dashed lines, the clock is low, so that pulse right there is completely ignored. Whatever the last value was that was captured on D stays on Q. All right. And then this period of time right here, where the clock is a logic 1, we take D, which is going for just a short period of time as a logic 0 and then hops up to a logic 1. So a short period of time as a logic 0 hops up to 1. There you go, until the clock goes to a 0 and that last value gets latched. And there you go. That is what the pattern would look like whenever you're having an active high transparent latch connected to those two inputs. All right. Lastly, let's figure out what an active low looks like. Now, the active low, as long as the clock is a 0, we're going to output just pass D straight through to Q. So the clock is a 0 for this period right here, which means this step up is going to be mapped from D to Q. Whatever the last value was, that gets latched, held on there. Now when the clock goes low again, this pattern right here where we go from a 0 for a while, then up to a logic 1, a 0 for a while and up to a logic 1. So this maps to that. Those two are the same. We'll connect that up right there. Then the clock goes high, and for this active low, when the clock goes high, we just hold on to the last value of Q. This period right here, where the clock is low, looks like we go for just a short time low, have a high pulse, and then back to low. So we go short time low, high, and then back to low. So that period right there, whatever D is equal to, Q is equal to the same thing. And then whenever the clock goes high on this active low D latch, we're just going to go ahead and hold on to the last value of Q. Then for this period right here, where the clock is a 0, that little short pulse gets mapped to Q. Clock goes high, we stay a logic 0, whatever that last value was that was latched. And then the clock goes low right here, and we have this high to low, and so we map that down to Q. Now, once again, all four of these guys are memory devices. They store something to Q based on the inputs that were in D and the clock. What do the outputs look like? What does Q look like? Depends very much on what the different type, whether it's, first of all, whether it's a flip-flop or a latch, and second of all, whether it's rising edge, falling edge, active high or active low. We're getting very different outputs here on Q. In the next lesson, what we're going to do is take some of these and show you some applications, some things we can do with these latches in order to support our computing.